My name is Yaga Richter. I'm a scientist at NCAR and a lead organizer of the NCAR Explorer series. It is my sincere pleasure to welcome you today to the MESA Laboratory and the third lecture in the NCAR Explorer series. NCAR, or the National Center for Atmospheric Research, is a world-leading organization dedicated to the study of the atmosphere, the Earth system, and the sun. Our scientists and engineers are very passionate about the work they do here, and through this series, they share their passion for scientific discovery with you and the global audience through our live stream and archive presentations on UCAR Connect. Thank you for taking the time today to join us. Today's speaker, Scott McIntosh, has a great passion for studying the sun, stars, planets, and galaxies, and you are in for a real treat. Dr. McIntosh was born in Uddingston, Scotland, a village of 10,000 people between Glasgow and Edinburgh, and attended University of Glasgow. As an undergraduate, he studied mathematics and physics and pursued internships in medical physics and medical imaging. Scott fell into astrophysics and solar physics by accident. He was convinced that the medical imaging skills he had learned could be applied to understanding the complex hot plasmas of the outer atmosphere of the sun and the stars. He then started his PhD in solar astrophysics at the University of Glasgow under the guidance of Astronomer Royal of Scotland. Dr. McIntosh was a postdoctoral fellow in NCAR's Advanced Study Program from 1999 to 2001. In 2001, Dr. McIntosh left NCAR to work with the European Space Agency at NASA Goddard Space Flight Center to be an instrument scientist for the Solar and Heliospheric Observatory, or the SOHO mission. From 2004 to 2007, he worked in Boulder at the Southwest Research Institute on a number of solar projects and missions. In 2007, Dr. McIntosh returned to NCAR and worked as a scientist in the High Altitude Observatory, or HAO. He quickly advanced to being the section head of HAO's Space, Weather, and Solar Transit Research Group, and since 2014 holds the position of the Director of High Altitude Observatory and Associate Director of NCAR. Dr. McIntosh is also an avid soccer player, coach, and fan. He and his 4 kids have set up their basement as a mini training facility so they can practice year-round. Scott has been known to coach more than one soccer team each season, so look for him at the St. Vrain's Football Club's games in the fall and spring. Please join me in welcoming Dr. Scott McIntosh.
Good afternoon, everyone. Hope you're all sitting comfortably. Take your glasses off, because you won't be able to see anything. Did I get the school teacher in to deal with you? No, I'm kidding. Good afternoon, everyone. So in the next 45 to 50 minutes, I'm going to give you a kind of a parade through some parts of our solar system, specifically the sun, the moon, and its interaction with us. And I hope to end with providing you some details about a small event that's going to happen about 350 days from now, just a little bit north of here, called a total solar eclipse. You notice here, beautiful image on the left is actually the first ever recorded picture of an eclipse, and it was taken in Königsberg, Prussia, in 1851. And it provides a kind of perfect slide. Like every bad talk, we must start with an overview. And so since this is going to be a bad talk, you must have an overview. So we're going to start with an overview of the sun itself. What is an eclipse? How did ancients think about eclipses? What are you seeing when you see an eclipse? Can we understand a little bit about the solar atmosphere? In doing that, we're going to take a small tour of the layers of the onion, the layers of our star, the sun, and then get to points where we start to think about how we're going to study certain pieces of its atmosphere. Before we dive into the reality of why do we study the sun in our technological society. A little bit about my home base, NCAR's Solar Terrestrial Physics Lab, or HAO, the High Altitude Observatory, before we dive in to the last 10 or 15 minutes or so on the 1st of August 2017 total solar eclipse, or as it was dubbed by one of my colleagues, the Great American Eclipse. Then, of course, to wrap up, I get to pose a challenge to the audience. You get to sit a test. If you fail the test, you don't get to leave the room. It's just my privilege. Okay. So as you may or may not know, we live in the atmosphere of our star. Our tiny little planet is bathed constantly with light and energetic particles that come from the sun. Now, we're kind of lucky. As much as we need that light to live and to grow food and to do just about anything, the energetic particles are profoundly destructive. They're profoundly destructive to any piece of electrical infrastructure, power grids, your laptops, your cell phones, anything that you would plug in is vulnerable because they're all connected to a power grid. Now, you will notice when this thing loops through that our little blue dot is protected. As these particles come streaming in from the sun 93 million miles away, you see they get deflected. It's kind of like, well, I guess it's not like bugs on your windshield, but they get deflected around our little planet. Can you see it there? Why is that? The clue comes in the next phase of the movie when the Earth gets hairy. The hairs coming out of the Earth are its magnetic field. And that magnetic field uniquely acts to save us from those particles from the sun. And if you don't believe me, I guess you should probably find a Martian to ask about the relevance of magnetic fields on their atmosphere.
Eclipse. The moon moves between the Earth and...
Do you want that? It's better than me. Okay, so what is a total solar eclipse? A total solar eclipse happens when the light... I'm going to jump this back, excuse me. A total solar eclipse happens when the moon blocks out the light from the sun. And by happenstance, the moon is 400 times smaller in diameter than the sun. But luckily, it's also 400 times closer to the Earth than the sun. So, at certain points in its orbit, it completely blocks out the light from the disk of the sun and leaves us with an astonishing image of something that you can't normally see unless you've got millions of dollars of really cool research hardware. Now, why does it do what it does? So it depends on 3 different cycles. What sets the eclipse? An eclipse has 3 components to it. If you want to predict it, you need to understand where the sun is relative to the Earth. That has a period of 364.25 days. You also need to understand where the moon is relative to the Earth and relative to the sun. And that has an orbit of about, or a period of about 27, give or take a day or half a day. And then you also have to understand where the moon is relative to the angle between the two. And it's in an elliptical form, and it wobbles north and south. And every now and again, those 3 things come into combination. And when those 3 things come into combination, you get a shadow on the Earth because now the moon and the sun are one, or they appear to be one in the sky. That shadow traces its way across the planet, and blocks out the light for several minutes for those that are sitting in the shadow. Now, if you're not directly in the shadow, you may be in what we call a partial eclipse. And in a partial eclipse, the sky won't go dark, the birds won't start chirping, the birds won't stop chirping, and several other things that you won't get. So if you can, get to totality. So there's several phases of a solar eclipse. There's a partial eclipse, when the moon first tries to take a bite out of the sun. Then eventually, as the moon transitions across from west to east, it starts to share a gradually more profound bite of the sun where Pac-Man is no longer there and you're left with a very faint crescent of light before the moon is completely eclipses the sun and you're left with a very faint halo around the sun. Does anybody know what that halo is called? The corona. Well, we've got some good people in here. We'll talk about the corona in the next slide. And before 1942 or thereabouts, the only way you could see the corona was from total solar eclipses. I'd like to say that now we have far more advanced technology that allows us to see it every day and study it in great detail. But of course, as the moon continues to pass across the face of the sun, we now start to see the reverse. And this is the part in a total solar eclipse when everybody just starts talking and going, woo, that's awesome. They forget about the poor third and fourth contact. They shouldn't be neglected. They're important parts in an eclipse too. So I mentioned the corona. Then we want to guess what drives the corona because I'm recording this. The corona is a very, very mysterious gas that exudes from the surface of the sun. And it's really a puzzle. In fact, it's one of the key cornerstones for our interaction with our star. And it really still puzzles us to this day, even though we've been observing it daily for almost 75 years. Now, we'll get to that in a minute. But what does a total solar eclipse look like from space? So here's a weather satellite that sits in a geosynchronous orbit around our planet. You can see that big shadow? That's not the Death Star. That is actually the shadow of the moon blocking out the light from the sun directly. And because you're in a geosynchronous satellite, of course, it's just sitting over one location, so it sees this shadow coming behind it. It's really beautiful, but imagine pretty eerie. Now, we also have a very cool piece of hardware out at the gravitational balance point between the Earth and the sun. It's about 1.5 million miles from here. There's an observatory called Discover. And that observatory called Discover has a telescope that looks back at the Earth. Now, that telescope looks back at the Earth every now and again, gets to be blocked out by the moon. And so this isn't Photoshop. This is real. It looks like Photoshop, but it's not. So back in the day, the ancients were kind of mysterious people, right? But the sun was even more mysterious to them. The moon was a mysterious body to them. And in fact, over millennia, they collected information about the stars and the planets and the moon and the sun, and started to even build things like Stonehenge up in the top left, which was actually a calendar. And that calendar actually could predict eclipses. Now, back